This is section 2.5, modeling direct variation. In the vocabulary here, we're going to start out by defining direct variation. A direct variation is a linear equation that looks like y equals a times x. The a in this problem is the slope, and the b, or I should say, I guess, the y-intercept in this problem is 0, which is why you don't see a number there. So y equals a times x. That's a direct variation. And anything that looks like that is a direct variation. So a direct variation basically means that you multiply x by some number to get y, and that's a direct variation. Now the a, even though that's the slope, if we were thinking of it as a linear equation, is also called the constant of variation. So that's the a value in that problem. So when we're working with direct variations, we call it a constant of variation. So again, the equation y equals a times x represents direct variation between x and y. And y is said to vary directly with x. The non-zero constant a is called the constant of variation. So once again, those are some vocabulary terms and phrases that we need to be familiar with. When we graph a direct variation, it is always a line. And again, the slope is the a, and the y-intercept is always 0. So it has to go through the origin. So it's the family of lines that goes through the point 0, 0. Those are direct variation graphs. So let's take a look at example number 1 here. It says write and graph a direct variation equation. So we're going to write and graph an equation, direct variation equation, that's important, that has the point -3, 2 as a solution. So we're going to use the given values of x and y. The x is -3 and the y is 2, to find the constant of variation, which is the a. So in this equation then, I'm going to replace y with 2 and x with -3. So 2 is equal to a times -3. Now we're going to solve this for a. So I got to divide by -3 on both sides. So a turns out to be the fraction -2/3. Now of course that's our slope. So the direct variation equation would read y equals -2/3 times x. So now that I've written that equation out, I want to graph it. Now we know that it goes through the origin. So we have a point here at the origin. We also know the slope is -2/3. So from that point that's on the line, if I go down 2 and right 3, this should be a second point. On the other hand, I could go backwards. I could go up 2 and left 3, and that would be yet another point. So if I was to graph this, the line then would go through those points. So there's the graph of y equals -2/3 x. The checkpoint that follows is a very similar problem, so just follow the example and see if you can do that one on your own. For example 2, we can use direct variations to represent the relationship between things in real life and solve problems. In this problem it says, according to Hooke's law, the force that is needed to stretch a spring varies directly with the amount the spring is stretched. Now, whenever we solve a direct variation problem, there's basically 4 steps to solving that problem, and I want to outline those steps here in the margin. So if we have a direct variation problem, step number 1, we want to write the general model for that direct variation. In other words, using the appropriate variables in the problem. Step number 2 then, we solve for the a, for the constant of variation. You are always given a pair that is already a solution, and based on that you should be able to figure out what a is. step number 3 then, we write an equation for the problem. Now, what we do then is once we figure out what A is, we plug it back into the general model to find that equation. And then step number 4, we can answer any questions that we have about the problem, such as to graph it, or maybe to find a value for the variable when the other variable is a specific value. So in this problem, again, it says, letter A, if 64 pounds of force F stretches a spring a distance of 8 inches, write an equation that relates F and D. So I'm going to use the information that I'm given to try to find that answer. So let's look at part A. It says here, according to Cook's law, the force that's needed to stretch a spring varies directly with the amount the spring is stretched. Now, with a direct variation, we know that y equals a times x is our general model. However, in this problem, we have variables that are f and d. So we're going to use the appropriate variables. So first of all, f equals a times d. That's the general model for this problem. Now, in the second part, we want to solve this thing for A. Now, I'm told that 64 pounds of force makes the spring stretch 8 inches. So I'm going to replace the F with 64 and the D with 8. So I'm going to say 64 equals A times 8. Now, I should be able to figure out what A is. I'm going to divide both sides by 8, and I get A is equal to 8. So now that I know what A is, I can write the equation for this problem. I can go back to step number 1, I can say the force F is equal to 8 times D. So here's the equation for this specific problem. That's the answer here for letter A. Now that I have that equation, I can find the amount of force needed to stretch a spring to 14 inches. So I'm going to use my formula here, F equals 8 times D. I need to slide this down a little bit. So I'm going to say F equals 8 times D. And this time I want to stretch the spring 14 inches. So that's going to be 8 times 14. And so this spring then needs a force of 112 pounds in order to stretch it to 8 inches. So there's the answer to the problem. So again, we have those 4 steps to follow, and if you follow those 4 steps in every direct variation problem, you should be able to come to the right answer pretty easily. Now, when we're working with direct variations, sometimes we're given data or information, and we have to determine if it fits a direct variation or not. And so in this problem, it says the table below gives sample cell phone bills showing the total monthly cost and the number of minutes used that month. Tell whether the total cost and the number of minutes show direct variation. If so, write an equation that relates the quantities. Now we know with direct variation that y equals a times x. Now, if I solve this thing for a, if I divide both sides by x, a is equal to y divided by x. But what is a? Remember, a is a constant. Excuse me. And so, if a is a constant, that means if I divide the y by the x, I should always get the same number. So in this problem, we're looking at this table. Now, actually, I think there's a mistake on here. I think the table is upside down. I think it should be flipped over. So I'm actually going to fix this. I'm going to put the 100 up here, 129, 229, 44, and 86. So I'm gonna flip that table over. Okay. So these are the minutes up here. So instead of x and y, actually, we're using m and c. And so if I take the y's, which are the c, and divide it by the x, which is the m, that should tell me what a is. So let's do that. So I'm going to divide the y, which is 35, by 100. So if I go 35 over 100, that's 0.35. Then I'm going to divide 45 by 129. When you do that, it's approximately 0.35. Then I'm going to divide 80 by 229. And guess what? It's approximately 0.35. And I'm going to do the same thing for the last two. And again, I get approximately 0.35 each time. Since I get the same answer every time I go y divided by x, I could say that this table shows a direct variation. And so, as I come down here then, the c divided by the m was always 0.35. So that means if I write this out as a direct variation, c would equal 0.35 times m. So that would be the equation for this problem. So again, the constant there can be found by dividing the y by the x. And then once you find that constant, that's the a in the problem, so you can just plug it in to write your equation. And that concludes section 2.5.